Year 12. I know that a lot of you last week said that you found the HL lesson a lot more challenging than the SL lesson, which makes perfect sense. So I thought that what I would do is record videos just going through some of the HL tasks, so that you've at least heard me explain those things, so that you can go through and check your work, and then when I look at your work, hopefully you'll understand what I mean when I'm adding comments on Manage Back. So you were asked to recall Fleming's left-hand rule. So this was taught at IGCSE if you were at the school last year, and remember that we use the left hand when it's the motor effect. So when we know that we have a magnetic field and we have a current carrying conductor, that's just a fancy way of saying wire, being placed into that magnetic field, we know that a force is then going to be felt by the wire. And the left hand rule allows us to work out the directions of what we have. So you may recall that if we see a cross, that's a way of representing an arrow going into the page. Obviously it's not possible to draw that in any other way. So just remember that the cross, the cross you can think of, if you imagine an archer with a bow and arrow, and you're flinging this across to hit a target. If you are looking at it from the point of view of the arrow coming towards you, you see a point. Okay, so the out of the page coming up out of the page towards your eyes, if you think about it, represented by the arrow head. If the arrow is away from you, so you're here looking at this arrow travelling this way, you can just see the tail feathers whistling away from you. So this represents the tail feathers, okay, so into the page. So in number 1 you can see we've got the magnetic field, which is our first finger, into the page. So we get our left hand rule at right angles, first finger into the page. We then swivel so that our thumb is in line with the force arrow, and my middle finger, which is current, now points to the left, and that's how we get that current is obviously travelling to the left. This is conventional current. In question 2, we've got a copper rod that's attached to a circuit, so I need to identify the positive terminal and the negative terminal of my battery. So you can see then that the current has to be flowing from positive to negative, so when this switch is closed, it's going to be flowing through this way. And so inside of the magnetic field, the current is coming towards you. So again, this time we've got the field, so that's our first finger pointing from left to right, from north to south. The current is coming towards me. This is in 3D. And now hopefully you can see that my thumb points up, so the force will be up. Then in question 3, we've got the field just simply going from left to right, so that's first finger again. The current is going away from me. Okay, you need to think about this in 3D. Okay, I can visualize this as field still going left to right, but if I'm looking at it from the point of view of kind of being stood here, the current is going away from me. Okay, so I swivel my middle finger to be going in line with the wire, but away from me, and my thumb now points down, so force is down. If you are struggling with this, it's really important that you get as much practice as possible, so let me know and I'll give you some more practice questions, because you do need to be able to use your left hand rule. Okay, question 4, the direction of the current that must be causing the force to act down. Well, we know that the field is going left to right, thumb is the force acting down, so now my middle finger is going into the page, so away from me. Okay, so this is the wire, so away from me is this way. And then again, if we have a force acting up, that's yellow, here's the wire, this is the current direction, which again is away from me. My thumb, force, my current is my middle finger, that's going away from me, so it's quite hard to show you this on a video. So we've got middle finger going that way, okay, that's the current. We've got the force going up. Okay, so now I know, let's see if I can get you to see this. This is my first finger. It's a bit wonky, but it's pointing generally to the left when my current's going in the page and my force is going up. So I know that I have to be going in this direction for my field, and field lines always point from north to south. Okay, so task 2. Hopefully you got on okay, at least with the symbol and the units, because they were just pulled from the slides. Okay, so we've got psi for flux, measured in Weber, n psi for magnetic flux linkage, also in Weber, and then flux density B, measured in Tesla T. So base units, let me just pull over a post-it note that I have so that I can fit everything on the page. So we know that for flux, the equation is given by BA, okay, and we'd already predefined B, so flux density, to be the force per unit current per unit length. Okay, now force again is not going to be measured in a base unit, so we need to break that down. F equals ma, force is mass times acceleration. Okay, so B can actually be found by mass multiplied by acceleration divided by current times length. Now all of these have base units, so mass is in kilograms, acceleration is meters per second squared, and then it's divided by current, so it's amps to the -1, and it's divided by length, so it's meters to the -1. And you can see that hopefully this m and this m cancel out. So the base units for flux density B will be kilograms seconds to the -2, amps to the -1. So that's where I get this one. Okay, and then I know that to get to flux and flux linkage, all I do is I multiply B by the area, and area in base units is just meters squared, okay, for the area bit. So I'm taking exactly what I did over here, but I'm just adding the term area there. So you can see again, mass is kilograms, acceleration meters per second squared, area meters squared, 1 over current, amp to the -1, 1 over length, m to the -1, and then I can gather like terms. So I've got 1m here, I've got 2 here, so that's 3. 3 minus 1 gives me 2, so I get m2 to end with, s minus 2, a minus 1. So that's how I'm getting my base units here. Okay, so just check carefully that you have got the same as me. Now, your definitions you may have had trouble with, but that's okay. This is me introducing to you how you can work out what definitions are. So flux was pretty straightforward. It's just the number of field lines passing through a given closed surface. Okay, and we know that flux linkage, what we're doing is we're taking the flux and then multiplying it by n, where n is the number of turns on a coil. Okay, and so the definition comes from the equation. We're multiplying these two things together, and therefore it's the product, which is just the multiplication of the magnetic flux through the coil, which is our flux here, and the number of turns on the coil, which is n. Okay, and then our magnetic flux density, that's where we go back to our original defining equation. B is F over IL. So it's the force per unit of current per unit of length. So that's where we get our numerical value from, but we need to extend that. So we've got the force per unit current per unit length, but we have to explain what that is acting on. So it's acting on a current carrying conductor, because remember that that can either be a wire or it could just be a moving charge, placed perpendicular to the magnetic field. So that's where our left hand rule comes in. Okay, for us to get the value of B, it's going to be when we have the magnetic field, let's say, going left to right, and our current has to be at right angles for us to get the correct value. Okay, So we're using our equations to define things in physics when we get to IB level. So just take a pause, make sure you've read through that, send me a message if you're still stuck. Okay, and now we're going to have a look at the IB practice questions. Okay, let's see if I can... Okay, so this looks deceptively difficult, but actually I think once you watch this video it should make a lot of sense. A rectangular coil rotates at constant angular velocity, so that means it's spinning round at a constant rate. At the instant shown, the plane of the coil, so remember plane, imagine like the plains of the Sahara Desert, I don't know, but basically the area that it is swept out by, so there's our plane. The plane of the coil is at right angles to the line Z, Z dash. A uniform magnetic field acts in that direction. Okay, so we know that the field, the magnetic field, is aligned with Z, Z dash. So what that tells us in reality is that we will have flux lines coming through. Oh, that's not very parallel, but you get the idea. Parallel to Z, Z dash. Okay, and so there are going to be flux lines cutting through this coil. What rotation of the coil about a specific axis will produce the graph of EMF, remember that this is just voltage, against time t. So remember that you saw a graph, and if I continue this graph, it's just a sine wave. And that was to do with how this coil rotates. Okay, so we know that for us to change the EMF, we have to change the amount of flux inside of the coil. Okay, so we know we have to cut through some of these field lines. I want to just quickly point out what it means by the pi over 2 and the pi. Okay, these are our values in radians. These are just angles, but they're in radians. Now hopefully from maths you already know that if we consider a full circle, we know that there are 360 degrees inside of a circle, and that is equivalent to 2 pi radians. So I've got this equivalency, so 360 degrees is 2 pi radians. If I divide both sides by 2, I get 180 degrees must equal pi radians, and 90 degrees must equal pi over 2 radians. Okay, now we know that we are going from 0 voltage to maximum voltage, and hopefully you remember from the slides that means that we have moved through 90 degrees. Okay, we get a shift every 90 degrees, so we can already rule out the ones that tell us to move through pi, okay, because we've moved too far. That would take us all the way back to 0. Okay, now what I want you to think about is if we rotate this coil around the ZZ axis, or if we rotate it around the XX axis. Okay, so if we take this coil of wire and we spin it around the ZZ axis, we are not going to change how many flux lines are inside of that coil. Okay, that's not going to work. But if we spin this coil of wire and bring it down and around, hopefully you can see, through the XX dash axis, it's going to cut through the flux. Okay, so we're going to go from having maximum flux as it currently stands to 90 degrees later it being in the plane. Let's see if I can kind of draw it a bit more obviously, where it's lying flat and the field lines are skimming, they're parallel, and so there aren't going to be any field lines that are cutting through that coil anymore. Okay, so that's when flux is 0, so that's when EMF is maximum. So we want to rotate around the XX dash, because if we rotate around ZZ dash, we're not actually changing how much flux is inside of our coil. Okay, so that gets us answer C is the correct answer there. Number 2 hopefully was a bit of respite for you. It's a lot easier because it's just remembering the units. So you can see some IB questions are easy. So magnetic field strength, remember, is represented by flux density B. So you just need to choose B there, please. In number 3, this one again looks deceptively difficult, but I think you'll quickly get your head around it. 3 conducting loops X, Y and Z are moving with the same speed from a region of 0 magnetic field. So currently these loops of wire are outside of the field, therefore no current is produced, there's no induced voltage. Into this magnetic field. Because we've got a dot, we know that the magnetic field B is into the page. Okay, and we're moving our coil of wire to the right. So we will get an induced EMF. Now we know that we will get maximum induced EMF and in terms of value when we're looking at the biggest change in flux. Okay, so cutting through the largest amount of flux is going to cause the EMF produced to be largest. So if I pick up all of these loops and I move them across, I want you to consider at the first instance where they're maybe here. Okay, so they haven't fully moved in yet, but they're on their way. So sometime later they've all shifted across. Hopefully you can see that at this first instant, this one is cutting through 1, 2, 3, 4 flux lines, whereas these are only cutting through 2. Okay, so we are going to say that loop Z is going to cause the largest induced EMF because there's more flux involved. Okay, obviously once we've got into the magnetic field fully, we're not actually changing how much flux we have anymore. So it doesn't stay this way, but because it says at the instant when the loops enter, we have an instant difference of 4 and 2, so we can choose Z at that point. Last but not least, number 4, you are given a coil, you're told the current direction in one side of the coil, so I've then just followed that round and shown you the direction of the current on each side of the coil. We can see that the magnetic field is into the page. They're kind enough to even say that to you, but you should recognise that from the crosses. Okay, so what we need to do is look at the force that is set up because we've got a current inside of a magnetic field. So we're going to use our left hand rule again, and we're basically just going to check which one works. Okay, so in this section, we've got the current, which is my middle finger, pointing up. Okay, we've got the argued force being towards the middle. Okay, and that would suggest, hopefully you can see, my finger's pointing out of the page. So this cannot be right because we know that it's into the page. In B, we do the same. So this time my middle finger goes across to the right, my thumb goes down. Again, my field is suggested to be out of the page, cannot be right. You can see where I'm going here. So third one, middle finger down, thumb, I can't actually do this on the screen because my elbow won't bend that way. Thumb goes to the left. Again, I'm getting my finger out of the page, it's no good. But lastly, my current pointing to the left, my thumb pointing down because the force is down. Now my field is going into the page, so this one matches what I know has to happen. So there you go. I will post separate solutions for Isaac Physics.